Okay. We ran out of time on Tuesday, so I wanted to just run over the last 2 or 3 slides, and then we'll jump into reviews. There's one type of reaction that is, well, extremely important, I would say, physiologically speaking, and that's a neutralization reaction. It involves acids and bases. Come on. Take control. There we go. So when you get an acid and a base reacting together, you have what we call a neutralization reaction. It's not a special reaction in terms of how you solve it, but sometimes it helps to recognize when you have a neutralization reaction and when you don't. Because then you're looking for indicators in the reaction to help you solve it. Every neutralization reaction has a net ionic expression equal to these. This is derived from the acid, this is derived from the base, and in combination they produce water. And that in fact is what drives the reaction, the formation of water. Because this is where the reaction wants to be, on that side. It will leave a few of these and a few of these behind, but most of it, the majority, the vast majority, will end up as water. That drives the reaction. Now, how we get the hydrogen ions and the hydroxyl ions together, that could be any one of 1,000 different combinations. Right? We could have something as simple as hydrochloric acid. So there's your proton combined with sodium hydroxide. And there's your hydroxide. The chlorine, the chloride ion, and the sodium ion are spectators. You could substitute anything in there as long as it's soluble and get the same net reaction. In this case, you'd still produce water, but you'd also produce sodium chloride in solution. And of course, we know that this molecular expression is actually sodium ions and chloride ions. Okay, so it's helpful to recognize and always appreciate that when you're working with an acid-base reaction, a neutralization reaction, this is where the business is happening, the protons and the hydroxyls. And you don't get lost in the confusion of the spectators. Okay, so here's an example. Sulfuric acid, we're going to react with sodium hydroxide. So there's sulfuric acid, which is soluble. Sodium hydroxide, also in solution. Okay, so we recognize that this sulfuric acid actually has 2 protons per molecule that can be neutralized with sodium hydroxide. So if we have 1 liter of this solution, and it's a concentration of 0.5 molar, Okay. And the question is, how many moles of sodium hydroxide are required stoichiometrically to react with sulfuric acid and produce water plus, and our spectators are sodium and sulfate. And so we have sodium and sulfate. The sulfate is a polyatomic ion with a 2- charge. Sodium is a +1 charge. So we have to have 2 sodiums to make that salt. And as far as terminology goes, maybe I better say a word about that. This is the acid, of course, because it supplies the protons. This is the base. It supplies the hydroxyls and accepts the protons to make water. And chemically defined, this is a salt. Okay. Anytime you react an acid and a base, you get water and a salt. Yeah, we normally think of salt as sodium chloride, table salt. But chemically speaking, anything as a result of an acid-base neutralization reaction produces water, and the leftover is salt, a salt. Oh, you could end up with an acidic solution? Okay, yeah, that's possible. If you have an excess of sulfuric acid, and this is the limiting, use it up, then you'll have some of this left over. Yeah, then you will have an acidic solution, correct. The other way is possible also. If you have more of that than you need, you could have a basic solution. Yep, that is true. So the question for this problem is, how many moles of sodium hydroxide are required to neutralize this much sodium sulfate? So what do we need? We need to know how many moles of sulfuric acid are here. Well, actually, we need a balanced equation first, don't we? We've got 2 sodiums over there. We need 2 here. Now we have 2 hydroxyls, and OH is over here. That should balance it, and we'll check ourselves. 2 hydrogens here, 2 hydrogens there, 4 hydrogens here. That balances. 2 oxygens here, 2 oxygens supplied from here. And of course, that oxygen remains within the sulfate. So we can exclude that from this calculation and say 1 sulfate here, 1 sulfate there. Right, so we're still balanced. Now, now we can determine how many moles are here, so we can find out how many moles there are required. So what was our expression for molarity? Number of moles divided by the volume. So if we want to know moles, we multiply molarity times volume. So molarity times volume is 0.5 moles of sulfuric acid. Now we can convert that to sodium hydroxide, find out how much is required. Just like any other equation, your conversion factor comes from the coefficients. So we have a 2 here and a 1 here. So it turns out we need that many mole of sodium hydroxide. Okay? Now that's the quantitative approach. We can get us, actually, a quantitative approach also works but this is more intuitive. If you recognize that this one produces 2 hydrogens for every 1 hydroxyl, then for every half a mole of this compound, it takes twice as many of this to neutralize those protons, right? Because this only produces 1 per.
What's a hydroxyl?
OH. That's a hydroxyl ion. That's a polyatomic ion. Yes, it's in that list.
Hydroxyl, the same thing as polyatomic.
It is a. Well, yeah, but there are other polyatomics. But the hydroxyl is a polyatomic. Right, it's one like this. Just like sulfate is like this. Other polyatomics like carbonate.
Is it just another name for it?
No, this is the hydroxyl ion. OH minus. Remember, you got a whole list of them in that. Yeah, you'll find the hydroxyls in there. Okay, so this answers the question of how many moles of sodium hydroxide are required. All right. Now, there's another unit of measure that is useful when we're talking about neutralization reactions. And I'm only going to approach this just as a point of information. And it's called normality, a big N. This one we have to be careful with, right? Because we do have an element with a single capital N. So we have to know our context. We're talking about acid-base reactions, and you see a big N, it means normality. Unless you find it in a compound, of course. But if you find it out separate from the equation with a number attached to it, that means normality. Now I have to define what normality means. First, we need the concept of equivalent. What is an equivalent? One equivalent of acid is that amount of acid that furnishes 1 mole of protons. Right? So, what's an equivalent of sulfuric acid? An equivalent of sulfuric acid is actually 1/2 of a mole. This 1/2 of a mole here, let's see, yeah, supplies 1 mole of protons. So this is an equivalent of sulfuric acid. 1 equivalent of a base is the amount of base that supplies 1 equivalent of hydroxyls. So for this one, only 1 hydroxyl per molecule. That means 1 mole of sodium hydroxide is equal to 1 equivalent of hydroxyls. Okay? I'm not going to dwell on this too much. The equivalent weight, if you know the molar mass of sulfuric acid, let's just calculate what it is. So the 2 of those, sulfur is 3207. I think I already know what it is because I've done this before. So that's 64 plus 32 plus 2. Is that 100? No, 98. So 98 grams per mole of sulfuric acid. So if you have 98 grams of sulfuric acid, you've got 1 mole of sulfuric acid. But how many moles of hydrogen ions do you have? 2. So this weight supplies 2 moles. And that yields 2 moles of hydrogen ions. So what would the equivalent weight would be? How much would it of sulfuric acid is required to produce 1 mole of hydrogen? Half of that, right? So 49 grams per equivalent. So only half of that mass would be required to produce 1 mole. That's what equivalent weight means. Okay, so this is the author's idea of, so if you have 1 mole of that, you get 2 moles of this. So that means a half a mole of sulfuric acid produces 1 mole. So this is the equivalent of sulfuric acid, which is a half a mole, to produce 1 equivalent. So for practical purposes, what we want to do is devise a concentration unit that will make acids and bases comparable. So normality is the equivalence of protons or hydroxyls per liter. Okay? That's what that means. The advantage to using this is you don't have to balance the equation. If you know the normality of your acid and the normality of your base, and the normality of your acid is 1, and the normality of your base is 1, then equal volumes will neutralize. That's the advantage of normality. And if you're in the business of doing these types of reactions and calculations day in and day out, normality is a good way to go. But if you're learning this for the first time in a chemistry class, sometimes the best way to go is to stick with molarity and use the balanced equation. You can't go wrong with that. Let's see. So here's our normality. Equivalents per liter is the definition. And it's just like any equation. Let's see, we need rather than N, which is moles, we'll say EQs for equivalents per volume. So if you need to know the number of equivalents you're dealing with, you just need the volume times the normality, and that'll give you the equivalence. Like any equation, you can solve for your unknown. And here we have the normality times the volume equals the number of equivalents. Okay, I don't want to take up too much time, but I think we're close to the end. That's the last slide. Okay, so we'll run through this slide, and then we'll move on to reviews. Okay, so if we have our compound is barium hydroxide, it's a strong base. Barium comes from the alkaline earths. So it's a 2+ charge. That means it needs 2 hydroxyls because each one of these is a 1- charge. So that's a balanced formula for barium hydroxide. The question is, if you have this many moles of barium hydroxide, how many equivalents do you have? Well, 1 mole of this, for each 1 mole of barium hydroxide, you get 2 moles of hydroxyls, which is 2 equivalents. So it's just 2 times 4 is 8. So if you have 4 moles of barium hydroxide, it can produce 8 equivalents in terms of acid-base reactions. Okay, so now we can move on to reviews. Close that out. All right. So let me minimize the amount of junk I have to shuffle in. Pull out these 2. Just a word about homework. I'm not going to follow you around with a whip and chair and try to force you to do your homework, the online homework. But just remember that that is worth 20% of your grade. Don't do any of your homework, you're just throwing away 20%. It's up to you whether you do it or not. Okay, now to the review. Come on. Hold it down too far. Might have to get up there and crank it manually. Hopefully I won't need that extra board. Okay. So if you have, does anybody run into a particular problem that we need to deal with before I start talking? There, this in here. Okay. I assume that I'm just going to have to start the ball rolling. Okay, so let's take something simple. How about number 2 first? You know, might need that one. Won't need this one for that problem. But we might need that information. So for number 2, the question is, no, that's not right. That's asking for mass. All right, so let's start with 1. I thought 2 was different, but it's not. How many grams of calcium chloride are needed to prepare 5.7 liters of 0.5 molar calcium chloride solution? All right, so we're dealing with calcium chloride, and we want it in solution, aqueous solution. You don't have to calculate the molar mass that's given to you. The target is molarity of 5.17, nope, that's volume. Molarity is 1/2. 1/2 molar calcium chloride is our target solution, and we want to end up with a volume of 5.17 liters. Okay? So what's the question? The question is, what mass do we need? Right? All right, so can we use that formula right now? Nope, not yet. Because this only term is in terms of moles, molarity, and liters. Right? So we've got to find out how many moles are required before we can answer this question. So we can find out how many moles. Will that get us any closer to the answer? Yeah. Oh yeah. Once you have moles, you can use this value to find out what mass you need. Okay. So if we solve this for moles, well, it's already solved for moles. So the number of moles then would be the molarity times the volume. And for this problem, that does have to be in liters. Right? When we were doing dilutions, we didn't have to adhere to that. But for this calculation, that definitely needs to be liters. So what do we get from that? Well, half of 5.17, I don't know if I can do that in my head. 2.585 moles. Well, hang on to an extra decimal until the end. So if we have that many moles, now we can convert that to mass, right? So if we have this, we just need a conversion factor that will give us grams. So that means grams on the top and moles on the bottom, right? So there's grams on the top, moles on the bottom. All right, 2.585 times 111. I get 287 rounded, because we have 3 significant figures here. So that's how many grams of calcium chloride you need to weigh out and dissolve it in a final volume of 5.17 liters in order to produce that molarity. Now, as a practical matter, is that going to be easy to do? No, because we don't have any glassware that's calibrated for exactly 5.17 liters. So if you actually go into the lab to produce a 0.5 molar solution of calcium chloride, your glassware is going to be limited to, say, a 1 liter volumetric flask or a 2 liter. I used to have a 4 liter, which is big and expensive. But you would just do 4 liters. And if you needed more, you'd set it up and do it with maybe a 2 liter flask. But it's difficult to produce a final volume for molarity without the volumetric glassware. The other thing you can do, I have done this before, you know the density. If the density of your solution, if your solution is dilute, you can assume the density is that of water. And you can calculate what's the mass, the final weight of your solution to give you that. All right, so that would be 5.17 kilograms. Because the density of water is, specific gravity of water is 1. So then you can set your beaker on a balance, and you can add this into a certain amount of water. After you tear your balance weight out, you don't want to weigh the beaker, not the balance weight, the beaker weight. And then you can add water until you get to 5.17 kilograms. And there you go. So the moral of that story is there's more than one way to produce a solution. You sort of have to improvise sometimes. If you absolutely have to have this volume. If you don't, then you use volumetric glassware and have extra. But this is a test problem. And lots of exam problems are kind of slightly removed from reality. Any questions on that? I think 2 is a similar type of problem, so we won't have to beat that horse. It just gives you a little extra practice. How about number 3? We'll do that one. So you have 3 liters of 3.67 molar sodium chloride solution, call that A. And you have 2 liters of 2 molar solution of silver nitrate. I can see where this one's going. You mix these solutions together and you make a solution C. Calculate the concentration of silver ions in solution C. Okay, so what do you need for a reaction balanced equation? So we're going to put these two solutions together. So the first solution starts out as sodium chloride in solution, right? And we're told that we have 3 liters of this one at 3.67 molar. And we're going to mix that solution together with this one, silver nitrate. And its particulars are 2 liters of 2 molar. Okay? And the final solution, the mixture of this. Now, what condition are we in here? Sodium ions, chloride ions, silver ions, and nitrate ions in solution. That's what aqueous means. If these are ionic compounds in solution, you actually have individual ions. So that means when you put them together, those ions have a chance to interact. Right? So the sodium could interact with nitrate, and the silver could interact with chloride. So that's what you get on the product side. Say the silver interacts with the chloride, and we check our charges, right? That's 1 minus, 1 minus, like that. So that means this one and that one, that's correctly written. And then the other is sodium and nitrate together. So the question is, what happens? Do we still have solutions here? Well, you look at the back, right? You find out if they're soluble. Sodium and nitrate together are soluble. And you look at silver and chloride and see if they're soluble. Let's see, there's silver. Silver is about a little past halfway across the top. And then you go down to chloride and you find out the box is grayed out, which means insoluble. So when you mix those two together, this is going to be transparent, that's going to be transparent because they're solutions. And then this is going to make your solution cloudy because it forms a solid. And if you wait long enough, that solid would just settle to the bottom of your beaker. This is called a precipitate, abbreviated like that. Okay, now back to the question. Calculate the concentration of silver ions. Well, what does that mean? Well, if that's true, if we do have some silver ions left over, that means all of the chloride had to be used up. There's no more chloride and you have some silver ions left over. Right? Maybe that's possible, maybe it's not. We have absolute amounts of each one, so one of them is going to be limiting. We just have to find out which one. So that means this is a balanced equation, right? It's just 1 to 1 to 1, 1 to 1 to 1, all the way across. So we need to know how many moles of chloride. Well, which one's limiting? Let's put it that way. Which one's limiting? So we need to know moles before we can go anywhere. So volume times molarity equals moles. So 3 times 3.67, right, should be, so I'm going to get my calculator out. Let's see. Oh, here we are. This is 11.01 moles of sodium chloride. And this is 4 moles of silver nitrate. Okay. So we could go ahead and do the usual, say how much product would each one produce. But look here, we can save ourselves some time. These are 1 to 1, right? So if they were going to be stoichiometric, these would have to be equal, wouldn't they? Right? It takes one of each, one of those to one of those. one of these to one of these. So this only requires, this much requires 4 moles of sodium chloride to be equal to that, right? 1 to 1, 1 to 1. So that means this one's limiting. It's going to run out. This one's excess. Okay? Now, what does that tell us about for answering the question? Calculate the concentration of silver ions. Do we have any silver ions left over? No, they're all gone. There's no silver left over. So the concentration of silver ions in solution is 0. We have completely consumed all the silver. So the moral of that story is, first, you need to recognize that this is reacted with that, producing that, so you can get your balanced equation. Then you find out how many moles of each one, and find out which one's limiting. Right? So the limiting one runs out completely. And once you know that this one runs out completely, that tells you that there's no silver left, and the concentration has to be 0. Okay? If it was the other way around, like we had this one over here and this one over here, then we'd have some excess silver. Right? You just have to calculate, say, how many moles. Well, let's say if the shoe were on the other foot, as they say, if this were silver nitrate, then you would have about 7 moles of silver nitrate left over. So you'd have 7 moles of silver ions because it's 1 to 1. And then it'd be 7 moles divided by how much volume? 3 plus 2. 7 divided by 5. Right? So that would be 1.4 molar of silver ions. Okay, if it were the other way around. But this way makes it easy. All you have to do is find out which is limiting. You see that silver nitrate ran out. There's only one possibility. That's why the answer is C, 0. Okay. Any questions? So it should become painfully obvious by now that previous chapters and everything you learned in the previous chapters are coming back to bite you if you don't have them firmly in hand. Because we're using things that we learned. Chemistry is a cumulative science. We build on the past. Okay. Nobody think of any other problems? Do I need to keep talking? I can do that. How about, let's see, make room here. How about number 5? What kind of problem is 5? What volume of 12 molar nitric acid is required to prepare 6.71 liters of 0.1 molar nitric acid? The dilution problem. I think in the slide we had M1 V1 equals M2 V2. So this would be the concentrated side, this would be the diluted side, usually. Doesn't have to be, because it's an equation. But you do have to make sure that you put the units, your values into the correct variables. And the best way to do that is to read the problem and say, what's what? So if we're going to say, what volume of 12 molar nitric acid is required? We can say this is the concentrated side, 12 molar nitric acid. And then the volume of that nitric acid we're going to use is the unknown. And the result you want is a concentration of 0.1 molar on the diluted side, and the volume you want to end up with is 6.71 molar. And here we are again, a hypothetical volume for which there is no known calibrated glassware to that volume. So this is an exercise in not futility, but exercise in concept. You know, do you know what you're doing? This is the real magic. Well, besides getting that formula, this is the real magic. Putting the numbers in where they're supposed to be first, then you can plug them in the formula. If you don't do that first, then you could pair this one with that one, and this one with that one, and then your ship is sunk. So we have 12 molar here. We have the unknown volume. We have the target concentration and its volume. Oops. Sorry. There we go. Now that we put everything in its proper place, it's just crunching numbers, right? So we would say this times this, which would be 0.671 divided by 12. And I get 0.05592 liters. Let's see, is the problem answer in liters? Yes, it's in liters. So we want to round it off to 3 significant figures. There you go. So that's the answer. That many liters. Just out of curiosity, how many milliliters is that? $55.9 milliliters. So that's how many, and the reason I do that is the volumetric glassware, or the devices, the pipettes, for instance, that you would use to remove this much of the concentrated acid to place it into your dilution flask, they're not calibrated in liters, they're calibrated in milliliters. So you would have to remove 55.9 milliliters with a properly calibrated pipette. The other possibility is if you know what the density of this is, then you can find out what mass you want, and you can weigh it out, and then dilute it. So, like I said before, there's more than one way to solve a problem. Well, what we would probably have is, I wouldn't even take a 4 and a 2. I'd take a 4-liter flask and a 4-liter flask. Just make up 8 liters. Then you would have more than you need. Okay, any questions there about dilution problems? Those are the kind of problems that I don't think doctors ever had to do that. Nurses, yeah. And lab techs, yeah, used to have to do these types of dilutions all the time to prepare their solutions. Now you don't have to do that. They make them for you. But that's how somebody had to do that. And then you or your employer has to pay for it. Let's see. See if I can find something else on a different concept. There's a lot of repetition, as usual. Number 8 is calculating the molarity. Well, let's just do that. Wouldn't hurt. Wouldn't hurt to hammer that nail again. as long as we don't run out of time. So we're given a mass of 47.7 grams of strontium chloride. And we're going to dissolve it in a volume of 112.5 milliliters. This is the volume of the solution. I said it wrong. Dissolve it in, we're actually producing that much solution after this goes into solution. That's required for molarity. You measure the volume of the final solution, not the volume that you put into the solution. Okay, so now the question is, what's the molarity? Okay, well, we need to know moles and volume, but we don't have moles, do we? We have to calculate moles. And that requires converting mass to moles. And so we have grams here, moles here. So we need molar mass. Anytime you see grams and moles in a quotient, that's molar mass. So strontium chloride, strontium's way over here, 8762. And chloride, we have two of them, which is 3545, memory serves. Yep. Okay, so now I need to do that little calculation. You guys check and be sure. Because if I make a mistake, and you make the same mistake, it doesn't cost me anything, but it can cost you points on it. Yes. So you gotta watch me. It looks reasonable. This is about 70, and that's about 80, so 150. So we'll put this in here, 58.5, and then we divide that number into 47.7. And I get 0.3009 moles of strontium chloride. Now we can fill our terms in. We got moles, we got volume, in, oops, that's milliliters. How many liters is that? Right, 1, 2, 3. 0.1125 liters. And if you haven't noticed before, anytime I have a decimal, that decimal never sits out here by itself. It's always got a zero bracketing in it. Without that zero, I call those orphan decimals. I don't like orphan decimals. I know I've heard from some of my students that in high school they say, who cares? You know, just put the decimal in the rest of the number. But in the real world, in the scientific world, you better have that zero there. If you try to publish a paper without that zero, then just throw it in the trash or send it back to you with red ink all over it. Okay, so now we got the moles. Okay, and then we got volume in the proper units of measure. So this one, and let's see, do I already have that? No, I don't have that yet. So I get in the neighborhood of rounded off 2.67 molar. Now, is that one of the answers? Yeah, that's E for number 8. Okay. Oops, everybody got this one. Also, sometimes you might want to compare this worked problem document with the way I do it, because I made this thing several years ago, And my method for solving the problem might be slightly different. In fact, it might be better now than it is there. But just keep an eagle eye on your instruction for discrepancies or improvements, whichever the case may be. I got 7 minutes, 8 minutes till 9. Okay, let's see, what else can we do here? Let's see, we've already done that one. Here's a concept problem, let's see. 15. No, that's not right. 10, excuse me. 10 is a concept problem. A mixture of sand and water is what? Actually, this takes us back to an earlier chapter. But sand and water, you know what's going to happen, right? But we need to apply a label to it. E is none of these. Is it an aqueous solution? Hardly. Is it a solution at all? No, not a solution. This is actually, the terminology is a mixture of. How about C? Is it a solute? No, because we're naming it as a mixture. Solute is a component. That's the minor component that goes into the solvent. Okay, so it's neither one of those. So the one left is none. It's not up there, right? Well, for argument's sake, what is it? Is it a mixture? Well, we said it was a mixture, actually. We got that part. Well, what kind of mixture is it? Heterogeneous. It's a heterogeneous mixture, which means everywhere you look in that mixture, you get a different composition, a different ratio of sand to water. No matter how hard you stir it, the instant you stop stirring, sand starts to settle. So if you sample at the top, you're likely to find no sand at all. But if you go to the middle or close to the bottom, you're going to get an increasing amount of sand for the same volume. That's a heterogeneous mixture. And actually, it's a morphing heterogeneous mixture. The longer you wait, the more contrast you get between one level and the other. That was kind of a review, really, of past concepts. Let's see, what else can we do that's useful? Let's see, this is one. Oh, no. 18. You guys are not ready for that one yet, I don't think, are you? No, because we don't get to gases till the next chapter.
We do 16.
16. Okay. 116.9 gram sample of nitric acid solution is 70% nitric acid by mass and contains, looks like the answer is in moles of nitric acid, okay? So we're given a mass of 116.9 grams of nitric acid solution. Right, so some of that Some of that mass is actually water. It's a solution. Right? But we're told the density, no, concentration of that solution is 70% HNO3 by mass. So it's like this, mass, which means 70% is 70 parts per 100, right? 70 parts per 100 parts. So 70 parts of nitric acid per 100 parts of solution. If we put mass and mass, they have to be the same units. So it'd be 70 grams of nitric acid per 100 grams of solution. Okay, that's probably what was giving you trouble. What does that mean? Okay, so now let's go back to the question. How many moles of nitric acid does that represent? Okay, in order to know how many moles, we have to separate out the actual amount, mass of nitric HNO3 from the solution, right? So if it's 70%, then we can convert mass of HNO3 per mass of solution. Right? This is the mass of the solution, right? This 8 is HNO3. So what did we say it was? 70 per 100. 70% is 70 parts per 100. Like that. 70 grams of HNO3 per 100 grams of solution. So now we can figure out how many grams of HNO3 we have. That's part of the solution. I get 81.83. Okay, so that makes sense. If it's only 70% HNO3 in that solution, this number should be less than that, right? If the number is bigger than that, then you know there's a problem. And the problem usually is you get those flipped. Okay, now we have exactly how many grams of HNO3 we have. We can convert that to moles. What we need is molar mass of HNO3. 1.01 for hydrogen, 14.01 for nitrogen, and 3 times 16 for oxygen. And 14.01, and 16 times 3 is 48. So I get 63.02 grams per mole. Divide that into that. I get 1 point. Let's see, we have. This is the conversion factor, so it doesn't count. So we're looking at that, 4 significant figures. 1.298 moles. What's the best? Does that one appear, or do we have to look for a best answer? 1.3, okay. So there's your best answer. Okay. Let's see. Okay, we're doing good on time. See what else we can come up with. 17 is a question of normality. Why don't we do that one? Okay, the question is, what's the normality of a base if, so we're looking for the normality of the base. What are we given to work with? We're given a volume of acid of 93.0 milliliters and a concentration or a molarity of the acid, actually. Yes, the molarity of the acid is 1.8 molar HCl. And we have a volume of base of 52.0 milliliters. Okay. So the normality of the base is going to be in terms of equivalence of base per volume, and volume in liters, actually. But here's another trick. The equivalence, let's see if I get this right. Yeah, required to neutralize. So the number of equivalents of base is going to be exactly equal to the number of equivalents of acid. Right? So equivalence of acid equals equivalence of base. Okay, that is the number of hydrogen ions equals the number of hydroxyl ions. So this term is equal to the normality of the base times the volume. Well, no, on this side, normality of the base times the volume of the base. And this one is the normality of the acid times the volume of the acid. Okay. Because this term is equal to that one, each one. Okay. So now let's see what we're given. Normality of the base. Okay, so this one's going to be the question. That's the question. The volume of the base, and notice also that this is a ratio, right? So we don't have to change the liters. If we were going to calculate this standalone, volume would have to be in liters. But for this ratio, it's like that other ratio, M1V1 equals M2V2. The volume doesn't have to be in liters because they're going to cancel anyway, right? They're equivalent units. So let's see, do we have the information we need? Well, let's see. Volume of the base, yeah, we have that, 52.0 milliliters. And we've got that side covered. How about this side? Volume of the acid, 93 milliliters. Okay. What's the normality of the acid? Is that true? Molarity is equal to normality if you've only got one proton per molecule. Okay? That's nice. So we do know what the normality is, 1.8 normal. So now we have our equation. So the hard part was recognizing that this is equal to that because it's neutralization. This is due entirely to the fact that it's a neutralization reaction, and we're looking for the stoichiometric ratio. How much? That the one equal 1 to 1. Equivalence of one equals equivalence of the other one. Then we fill in the equation and look for the values. So now this is going to be like that. We can solve for this one. So in the normality of the base is actually this times that divided by this. Okay. So let's see, 1.8 normal. 93 mils. So I get 3.2 normal for the base. So which one was it? 17. Yeah. At least it agrees with the answer sheet. 3.2 normal. It just takes some getting used to. I mean, 2 days ago I threw molarity at you, and now it's morphing into normality. You know, so I can see where that can be confusing, but it's really a simple concept. Molarity is an absolute amount of moles of something, no matter what it is. Normality takes into account the structure. How many protons can you produce from that mole? Or how many hydroxyls can you produce from that mole? And that modifies normality from molarity. In this case, it was great. It was 1 to 1. So they were equal. Let's take a hypothetical. What if this were sulfuric acid? What would its normality be? 1.8 molar sulfuric produces twice as many moles or equivalents of hydrogen as that suggests. So its normality would be 3.6. Oops. That was wrong too. Should have been normal. Okay. So if you know the molarity of sulfuric acid, the normality is twice. Because for each one, you're producing 2 protons. Then it just plugs into that formula just like any other. I mean, it doesn't matter, acid base. If you know the normality, it doesn't matter where it came from. Okay, so let's work it backwards the other way. Suppose, let's work this problem backwards. Suppose the acid we want, suppose we want the acid to be 1.8 normal, and it happens to be sulfuric. What molarity of sulfuric would give you that normality? Right, this is the number of equivalents per liter of hydrogen. So what molarity would give you that many equivalents? Half as much, right? Half as much. 0.9 molar H2SO4 would give you 1.8 normal. Okay. All right. Let's see what other trouble we can get into here. Sometimes it's easier to look at the work problems and I can pick out the differences in concept here. What about 22? 22 give anybody trouble? Assuming you made it that far. Right. I know it's only been 2 days. But let's look at it anyway. 22. Which of the following solutions contains the smallest number of ions? So that's what we're looking for, the smallest number of ions. So here are I see Henry Ford in our future. 246.8 milliliters. 6.8 milliliters of 1.0 molar sodium sulfate. Okay, it gave you the name, but it didn't give you the formula, right? So you got to write the formula. Sodium and sulfate. Now we got to write it correctly. 2 minus charge, 1 plus charge. Takes 2 of those. 539.8. 8 milliliters of 1 molar lithium nitrate. Lithium nitrate. Okay, so let's see. We know nitrate is a polyatomic with a 1 minus charge. Lithium comes from here. 1 plus charge. That's it. 1 to 1. Right. Minus C. 305.6 milliliters of 2 molar potassium hydroxide. There's another polyatomic. Minus 1, plus 1. That's good. D is 189.6 milliliters of 2 molar iron 3 chloride. So that means iron has a charge of 3 plus combined with chloride with 1 minus, which means 3 chlorides. Okay? And E, at least 2 of the above contain the smallest number. So that's just saying 2 of the above are equal. Equal ions and smallest. Okay. The only way to know that one, whether the E is true, is to do the calculations. All right. So, what's the ratio? Molarity equals moles over volume. So moles equals molarity times volume. Okay, Henry Ford coming down the line. So here's volume, here's molarity. Now, I threw millimoles at you before, didn't I? Okay. If you just multiply milliliters times molarity, you get millimoles. You know, and if we're going to solve this problem for smallest number of ions, it doesn't matter if we're talking about moles or millimoles. As long as we use the same units, we can find out the smallest number. Right? So we can save ourselves a step. Instead of changing this to liters, just say each one of these times its molarity. Right. So 1 is 246.8 millimoles of compound. And this one is 539.8, 39.8 millimoles of compound. This one is 2 times that. Let's see if I can do that one in my head. I have to go backwards. Is that right? Yep. So that's millimoles of compound. And this one is 2 times 189.6. I can do that with my hand. 17.3. Oh, somebody's alarm. I hate those things. One of these days, I'm going to have to buy a new car. And I'm sure it'll have By that time, it'll have all this stuff standard. So I'll have to find out how to disable it. Okay, so that's only the amount of compound. How many ions, right? So how many ions does this compound produce? 1, 2, 3. So this is ions per mole of compound. Yeah. This one produces only 2. This one produces 2. Means this one produced 4. Now we can compare ions. So I don't want to have to do that one in my head. 246.8 in there. So this is 740.4. This is millimoles of ions. And 539.8 times 2 is 1,079.6 millimoles. And this one, then maybe I can do this one in my head. 0.4, 12. And 4 times that one is 1,516.8. That's all millimoles of ions. All right. So the least number is the first one, right? This is the first one. That means E's not it. A. Yeah. Agree with the answer sheet. That's always a good sign. If I don't agree with the answer sheet, then I've got to go say who's right.
You know, you have a group, a Jeep Laredo, Grand Cherokee, English color.
Mm-hmm. Not in here.
I think you
You
did.
do?
That might be yours.
Do you have one?
Not a Grand Cherokee.
Oh. She didn't say a green Cherokee? Green.
Yeah, Jeep Laredo.
Jeep Laredo. You don't have a Laredo. Okay. We're good.
It stopped anyway, so that's good.
Are they supposed to stop after a while and then maybe start up
I think you
again?
have to do it. Yeah, I'm pretty sure.
Or till the battery's dead?
I never lost my cars. Me neither.
Is it not worth much?
No, no, the body is, I just.
Okay. So that's the way Henry Ford would solve this problem. Assembly line. Okay. Let's see what else we can find that's useful. Okay, 26 is like that earlier problem where we reacted silver nitrate, sodium chloride. Only in the case of 26, the silver nitrate is in excess. So we're only going to use up some of the silver ions, and some of them left over, then we calculate the concentration. So we'll come back to that if we have time. But I've already shown you how to solve it anyway. I want to be sure we don't miss any useful topics here. Where's 29? Okay. We'll come back to 29 too if we don't find anything else that's different. work from the back. How about 72? Let's do that one. That's a neutralization reaction. And we're going to calculate the molarity of the hydrogen ions. Have we done pH in this class? Do pH? Let's see if we have that. I can't imagine that I would leave that out. Chapter 16. Acids, bases, and pH. Okay. So we will do that eventually. That's good to know. What did I say? 72. 72. I went too far. Back up one page. All right. So we're going to mix two solutions. First one is a base, 100 milliliters of 0.1 molar sodium hydroxide, and 150 milliliters of 0.104 molar hydrochloric acid. Then we're going to determine the concentration of hydrogen ions in the final mixture. Now that assumes that the acid is in excess and we have some hydrogen ions left over. So we've got to prove that first. Right? So the reaction is going to be sodium hydroxide plus hydrochloric acid yields water plus sodium chloride. Okay, and fortunately, it's already balanced. So we write in what we know. Sodium hydroxide, 100 milliliters of 0.1 molar. And hydrochloric is 150 milliliters of 0.104 molar. And then the question is, what's the hydrogen ion concentration? So this is in solution, this is actually that plus that. So what we have to do is find out how many moles of this, how many moles of that. And since they're 1-to-1, if it's stoichiometric, they have to be equal. But if one of them is bigger, then that's the one that's excess. And that will tell us whether we have any extra hydrogen ions or not. So this is going to be 0.1 times 100 is 10 units, millimoles, milliliters, millimoles. Okay, and this one is, it would have to be an odd number like that. Well, not odd, but different. Mathematically speaking, it's an even number. So this is 15.6 millimoles. Okay, there's the answer to our question. We have excess acid. That means we are going to have some hydrogen ions left over. How many? Well, if it's 1-to-1, 10 millimoles will be used up. And leave us with 5.6 millimoles of hydrogen ions, because it's 1-to-1. This many millimoles of that is this many millimoles of that. So now we know how many millimoles of hydrogen. And here's the other trick. If you divide millimoles by milliliters, you get molarity. Did I show you that last time? Moles per liter equals molarity. So can millimoles per milliliter equal molarity. Well, how do you get millimoles from this? 10 to the minus 3? Right, 1,000th of this is a millimole. How about liters to milliliters? 10 to the minus 3? Same thing. We just had to prove it to you. Okay, so if we divide this by the total number of milliliters, which is what? 250. 100 plus 150. Right? So that should be, let me just use my calculator. Zero point 0.224 molar hydrogen ions. A. Now, when we get to the chapter on acids and bases, we're going to take this another step. So once you know that value, you can calculate the pH. But I don't want to muddy your minds with information that you don't need right now. That answers the question. Okay, how are we doing on time? Yeah, 10 more minutes?
What time was it?
I got 9:30 or 9:29.
Well,
Let's see here.
we do 60.
69, okay. Those mass percents give you trouble, don't they? All right, 69. The total mass of a solution is 184. The mass of the solution equals 184.8 grams. Okay. The solvent mass is 152. So mass of the solvent is 125.2 grams. What's the mass percent? Okay. The total mass of the solution is composed of what? Solvent and solute. Right. The calculation of percent by mass equals the mass of the solute divided by the mass of the solution times 100. Right. So we have the mass of the solution right there. We need the mass of the solute. How do you find the mass of the solute? Well, we're given the solvent part, and this is composed of the mass of the solute plus the mass of the solvent. Right. Okay. Oh, all right. Yeah, we're about finished. Everything will read on the whiteboard this evening. Okay, see where I'm going with this? We know this one, and we know this one. So all we need is to subtract that one from that one to get this one, right? Because this is the summation of those two. So the mass of the solute is equal to 184 minus 125. Oops. let's see, which would be 59.6 grams. Okay. And then we just plug that into the formula. Percent mass is 59.6 divided by solution, 184.8 times 100. So I get 32.3%. Okay. Yeah, sometimes the information you need is sort of buried in the problem. You got to dig it out. This is really a test of whether you understand how this formula is constructed. The mass of the solute is both in the numerator and the denominator because it has to be included as a part of the whole. All right, we got about 5 minutes left. Here's one the students miss. Strange. Because they're just definitions. And actually they're intuitive. When a solvent has dissolved all of the solute it can at a particular temperature. So maximum amount of solute dissolved. That's what they're saying. The maximum amount of solute dissolved is which one of these? Unsaturated, supersaturated, none of these, saturated, or diluted. All right. Definition. If you've got the maximum amount of solute dissolved at temperature, specific temperature, you have a saturated solution. Right? What if you have less than that amount, less than the maximum amount? You have an unsaturated solution. What if you have more than that amount at that given temperature? Supersaturated. Okay. And diluted is sort of a special case all by itself. You would have to have a very, very small amount of solute dissolved in your solvent to be diluted. But if you had a lot, and this is relative terms, a lot of solute in your solvent, and that would be based upon what's the maximum it can hold, then it would be concentrated versus diluted. Okay. Well, I don't know what else to talk about. Guess I'll see you on Tuesday. Let's see here. Stop the